Welcome. Find a comfortable position, let your body settle, and allow your eyes to gently close. Over the next hour, we're going to take a quiet journey together along the changing coastlines of our world, exploring a phenomenon both beautiful and unsettling, a transformation happening right now on shores from North Carolina to Australia, from Canada to Bangladesh. We'll walk among forests that are no longer alive but still standing, gray sentinels rising from wetlands and shallow water. We'll learn how they form, why they matter, and what they tell us about our changing planet. We'll meet the scientists who study them, the communities affected by them, and the unexpected life that finds ways to thrive among the dead trees. This is a story told slowly, meant not to alarm but to inform, not to disturb your rest but to accompany it. Let the words wash over you like gentle waves. There's no need to remember every detail, no test waiting at the end. Simply listen, let your mind wander where it will, and allow sleep to find you whenever it's ready. The journey begins now, with a walk along a familiar coastal trail, where something has changed. The haunting discovery. Imagine walking along a familiar coastal trail, one you've known for years. The path winds through what was once a thriving forest, thick with green leaves and the sounds of birds calling to one another. Perhaps you walked the same path as a child, or maybe you discovered it more recently, but either way, it became a place you returned to, a place that felt constant and reliable. But today, something has changed. The landscape before you is transformed into something altogether different, something that stops you in your tracks and makes you pause to take it all in. What you're seeing are ghost forests. Coastal landscapes filled with dead, standing trees. These are not fallen logs scattered across the ground, not stumps waiting to decay into the earth. These are trees that remain upright, their trunks still reaching toward the sky, but stripped of life. They often look like gray, leafless skeletons rising from wetlands and marshes, their bare branches extending outward like fingers grasping at something that's no longer there. The bark has faded to silvery gray, weathered by salt and sun and wind. Some trees stand perfectly straight, as if frozen in time. Others lean at odd angles, their root systems weakened but not yet ready to surrender completely. Many visitors who encounter these places for the first time describe ghost forests as eerie, lonely, and otherworldly. There's something about the silence among those standing dead trees, the way light filters through branches that will never again hold leaves, that creates an atmosphere unlike anything else in nature. The usual sounds of a forest, the rustling of leaves in the breeze, the scurrying of small animals through undergrowth, the chorus of insects on a summer evening, all of these have faded away. What remains is a different kind of quiet, deeper and more complete. Perhaps you hear only the gentle lapping of water against the bases of the dead trees, or the distant cry of a seabird passing overhead. In regions rich with folklore and old stories, ghost forests blend easily into ghost stories. They become the settings for local legends, places where people whisper about strange sightings and unexplainable feelings. In some communities, parents tell their children to stay away from the ghost forests, not because of any real danger, but because the places feel wrong somehow, as if the natural order has been disrupted. The trees themselves become characters in these stories, silent witnesses to the passage of time and change. The haunting appearance of these forests can cause people to avoid these areas for recreation. Where families once hiked and children once played, where couples once walked hand in hand through dappled shade, there's now a reluctance to enter. The visual impact is profound, unsettling in ways that are hard to fully articulate. It's as if the landscape itself is telling you that something has gone wrong, that something has been lost that can never be recovered. The psychological weight of standing among hundreds or thousands of dead trees, all of them victims of the same slow catastrophe, can feel overwhelming. For local residents who have watched their familiar forests transform over months and years, the experience goes even deeper. They often describe an emotional grieving process as the forests disappear. These aren't just trees dying in some distant wilderness that they've only seen in photographs. These are places connected to memories, to childhood adventures, to quiet moments of peace. Perhaps this was the forest where someone proposed to their partner, or where a family scattered the ashes of a loved one, or where a child first learned to identify different types of birds. Watching these places fade into gray sentinels is like watching a part of your own history slowly vanish. Some people describe feeling anger, others describe sadness, and many describe a sense of helplessness in the face of forces too large to control. In our modern age of connection and sharing, social media spreads ghost forest images widely across the internet, increasing public dread and curiosity in equal measure. A photograph of those skeletal trees standing in still water can travel around the world in moments, each share carrying with it questions and concerns. What happened here? Could this happen where I live? Is this the future that awaits other forests? The images are powerful precisely because they need no explanation to convey that something significant has occurred. Even someone scrolling quickly through their feed will pause at the sight of a ghost forest, struck by the stark beauty and implicit tragedy captured in the frame. Artists and photographers have discovered in ghost forests a compelling subject, turning these landscapes into symbols of loss and change. Through their lenses and brushes, ghost forests become more than just dead trees. They become visual poetry about transformation, about the passage of time, about the fragility of the world we think we know. A photographer might wait for the perfect light, that golden hour when the sun sits low on the horizon and casts long shadows across the wetland, illuminating the dead trees in warm tones that somehow make their death even more poignant. A painter might choose to emphasize the contrast between the gray, lifeless trees and the vibrant sky above them, or the rich green of marsh grasses growing around their bases. In galleries and exhibitions, these images speak to something universal in the human experience. The understanding that nothing remains unchanged forever, that even the seemingly permanent can fade away. But people don't only observe and document. Some communities have begun to create rituals like tree planting memorials to reclaim agency in the face of these losses. When a forest dies, they plant new trees elsewhere, often native species better adapted to the changing conditions. When the landscape changes beyond recognition, they gather together to acknowledge what was lost and to actively participate in creating something new. These rituals serve both practical and emotional purposes, reminding people that while they cannot stop every change, they are not entirely powerless. A group of neighbors might meet on a Saturday morning, shovels and saplings in hand, working together to create something that will outlast them, to give the future a gift even as they mourn what the past has taken from them. Interestingly, ghost forests have even inspired what some call ghost tourism in certain coastal areas. People travel specifically to see these haunting landscapes, to stand among the dead trees and contemplate what they represent. It's a peculiar form of dark tourism, drawn not to sites of human tragedy, but to places where nature itself bears witness to profound environmental shift. Tour guides lead groups through these areas, explaining the science behind what happened, the gradual encroachment of salt water, the way the trees struggled and ultimately failed to adapt. Some visitors come with cameras, hoping to capture the strange beauty of these places. Others come simply to be present, to bear witness, to let the reality of what they're seeing sink into their understanding of the world. For many people now, ghost forests have become visual proof of climate change. They are tangible, impossible to ignore, standing right there in the physical world rather than existing as abstract data or distant predictions. You can walk among them, touch the gray bark of dead trees, and understand with your own senses that the world is changing in fundamental ways. Numbers and graphs and scientific reports are important, but they live in the realm of the intellect. Ghost forests speak to something more immediate, more visceral. They are proof that can be witnessed with your own eyes. This is why they are often called canaries in the coal mine for rising seas. Just as miners once brought canaries underground to detect dangerous gases before they became lethal to humans, ghost forests serve as early warning systems for coastal communities. They show us what's coming, what happens when salt water pushes too far inland, when the delicate balance that allowed these forests to thrive is disrupted. They stand as silent witnesses to changes that will eventually affect not just trees, but all of us who live along the coasts. What happens to the forests today may happen to coastal towns and cities tomorrow. The trees are telling us something, if we're willing to listen. 1. What ghost forests really are. Now that we've walked among these strange and haunting landscapes, let us take a moment to understand what ghost forests truly are, how they come into being, and what forces shape them into the stark monuments we see standing in coastal waters and wetlands. Ghost forests form when coastal woodlands begin dying while still standing. This is a crucial distinction, one worth pausing to consider. These trees do not fall in storms. They are not harvested by human hands. They are not consumed by wildfire or felled by disease in the traditional sense. Instead, they die where they stand, remaining upright even as life drains slowly from their roots, their trunks, their branches. They become monuments to their own demise, testimonies written in wood and bark to the changing conditions around them. The most common cause is rising sea levels and saltwater intrusion. Around the world, in coastal regions from North America to Europe to Asia, the story is remarkably similar. The ocean is rising, slowly but persistently, and as it does, salt water pushes farther and farther inland. It seeps through soil, travels up estuaries and rivers, infiltrates groundwater systems that once held only fresh water. This process might seem abstract until you witness its effects, until you see an entire forest transformed by the gradual advance of the sea. Salt water poisons many trees because they depend on fresh water in the soil. Think about what a tree needs to survive. It draws water up from the ground through its roots, water that carries dissolved nutrients essential for growth and life. This system evolved over countless generations in environments where the water was fresh, where salt concentrations remained low enough that the tree's internal mechanisms could function properly. But salt changes everything. When salt water infiltrates the soil, it disrupts the delicate osmotic balance that allows roots to absorb water. The salt essentially locks the water away from the tree, even as the tree stands surrounded by moisture. It's a cruel irony, a slow death by thirst while drowning in salt water. Trees usually die slowly over years as salinity builds up. This is not a sudden event, not a catastrophe that unfolds in days or weeks. Instead, it is a gradual weakening, a progressive decline that might not even be noticeable at first. In the first year, perhaps the tree produces slightly fewer leaves. Its growth rings become narrower, though you would need to cut into the trunk to see this. The following year, some branches might remain bare when spring arrives. Birds that once nested in the canopy choose other trees. Year by year, the decline continues. The bark begins to change color, fading from rich brown to weathered gray. Leaves appear later each spring, fall earlier each autumn, until finally, one year, they don't appear at all. The tree has died, but it remains standing, a ghost of its former self. Waterlogging and rising water tables can also kill trees, even before full seawater flooding occurs. Sometimes the problem isn't salt at all, at least not initially. In some coastal areas, the water table, the level below which the ground is completely saturated with water, rises as sea levels increase. Tree roots need to breathe, to access oxygen in the soil. When the water table rises too high, it drowns the roots, suffocating them even in the absence of salt. This can happen in areas that seem far from the ocean itself, places where people might not immediately connect the dying trees to rising seas. But the connection is there, invisible beneath the ground, written in saturated soil and oxygen-starved roots. As forests die, they are often replaced by marsh vegetation. Nature abhors a vacuum, as the saying goes. When the trees disappear, other plants move in, species better adapted to the new conditions. Salt marsh grasses, cordgrass, and other wetland plants that thrive in salty, waterlogged conditions begin to colonize the spaces between the dead trees. These plants have evolved different strategies, different mechanisms for dealing with salt and standing water. They spread their roots through the wet soil, their green growth providing a stark contrast to the gray, dead trees rising above them. In time, these grasses may completely carpet the forest floor, transforming what was once woodland into wetland. Over time, some ghost forests transition into open water. The process doesn't stop with the death of the trees. The standing dead trunks, exposed to weather and waves, gradually weaken. Some eventually topple, crashing into the marsh or shallow water where they will slowly decay. Others rot from the inside, becoming hollow shells that finally collapse in on themselves. As this happens, as the trees disappear and the land continues to sink or the water continues to rise, open water claims more and more territory. What was forest becoming marsh? What was marsh becoming shallow bay? The landscape is rewritten entirely, transformed beyond recognition. Not all ghost forests come from modern climate change alone. This is an important truth to understand, a reminder that while our current crisis is urgent and real, the forces that create ghost forests have existed throughout Earth's history. Some ghost forests visible today are ancient, the products of changes that occurred hundreds or even thousands of years ago. Others form through entirely different mechanisms than gradual sea level rise. The world is complex, and multiple forces can create similar outcomes. Some ghost forests form when land suddenly drops during earthquakes, submerging forests in a matter of moments. In tectonically active regions, the ground itself can shift dramatically. An earthquake strikes, and in its aftermath, coastal land that once stood above sea level has dropped, sometimes by several feet or more. Suddenly, trees that grew in well-drained soil find themselves standing in salt water. The death that follows may be just as slow as in forests affected by gradual sea rise, but the initial transformation happens not over decades but in seconds. These seismic ghost forests serve as markers of geological catastrophe, frozen moments of tectonic violence preserved in dead wood. Ghost forests can form slowly from sea rise or suddenly from subsidence events. Subsidence is the gradual or sudden sinking of land, which can happen for various reasons. Sometimes it occurs when groundwater is extracted faster than it can be replenished, causing the land above to settle and compress. Sometimes it happens when organic-rich soils, like peat, dry out and compact. Sometimes it results from the removal of oil or gas from underground reservoirs. In any of these cases, the land surface drops, and what was once above the reach of tidal waters may suddenly find itself regularly flooded. The effect on trees is the same whether the water rises or the land falls. The forest becomes a ghost of itself, a gray memorial to what once grew green and vital. Understanding these mechanisms, these various pathways through which a forest can become a ghost forest, helps us appreciate both the complexity of what we're witnessing and the urgency of the moment. Some of these processes are natural, part of the Earth's long history of change and transformation. Others are accelerated or caused by human activity, by the carbon we've released into the atmosphere, by the groundwater we've pumped from beneath our feet, by the ways we've altered the landscape to suit our needs without fully considering the consequences. How the coast turns a forest into a graveyard. To truly understand ghost forests, we must follow the journey of salt water as it makes its slow, relentless advance inland. We must understand the forces that push it forward, the barriers that slow it down, and the complex dance between land and sea that ultimately transforms living woodland into silent graveyards of standing timber. Rising seas push saltwater farther inland than before. This is the fundamental driver, the engine behind so much of what we see in coastal ghost forests. The ocean is rising, measurably and persistently. Each year, on average, sea levels climb a little higher. The increase might seem small when measured in millimeters, barely noticeable in any single year, but these small increments accumulate. Over decades, they add up to inches, and those inches make all the difference. Salt water that once stopped at the edge of a tidal creek now flows into areas that were previously safe. High tides reach farther. Storm tides reach farther still. And with each incursion, salt deposits itself in soil that evolved to support freshwater-dependent species. Storm surges accelerate the process by flooding forests with salt water in sudden, overwhelming pulses. While gradual sea level rise provides the baseline, the steady pressure that pushes salt water inland year after year, storms deliver acute shocks to the system. When a powerful storm approaches the coast, it doesn't just bring wind and rain. It pushes a massive dome of ocean water ahead of it, a surge that can raise water levels by 10, 15, even 20 feet or more above normal. This surge doesn't respect the usual boundaries between sea and land. It flows over beaches, across dunes, through coastal communities, and deep into forests that might normally stand well above the reach of tides. When the storm passes and the water recedes, it leaves behind salt, deposited throughout the soil, coating the roots of trees, fundamentally altering the chemistry of the forest floor. Hurricanes can rapidly expand ghost forest zones in a single season, transforming landscapes in ways that would otherwise take years or even decades. A forest that appeared healthy in the spring might be visibly stressed by autumn if a major hurricane passes through during the summer. The trees don't necessarily die immediately. They may leaf out the following spring, drawing on reserves built up over previous years. But the damage has been done. The salt remains in the soil. Each subsequent storm adds to the burden. Each high tide brings a little more salt. The trees are wounded, weakened, set on a trajectory toward death that may take several more years to fully unfold. Hurricane Irene in 2011 helped drive major ghost forest expansion in North Carolina, serving as a dramatic example of how a single storm event can accelerate processes that were already underway. Researchers studying coastal forests in the region documented significant increases in tree mortality in the years following Irene. Forests that had shown early signs of stress suddenly tipped past the point of no return. The hurricane didn't create the ghost forests alone, but it acted as a catalyst, pushing vulnerable ecosystems over the edge. Scientists were able to use this event as a kind of natural experiment, studying how trees responded to the sudden influx of salt water, documenting which species proved most vulnerable and which showed surprising resilience. Flooding raises soil salinity beyond what most trees can tolerate, and the tolerance levels vary considerably from one species to another. Some trees, particularly those that evolved in coastal environments or in areas with naturally high groundwater salinity, can handle moderate amounts of salt. They have developed specialized cells that can sequester salt away from sensitive tissues, or mechanisms to excrete excess salt through their leaves. But most trees common to temperate forests, oaks and pines and maples and countless others, have no such adaptations. They evolved in environments where fresh water was abundant and salt was rare. For these species, even relatively low levels of soil salinity can prove fatal. The precise threshold varies, but once it's crossed, the tree's fate is sealed. Salt stress weakens trees long before they fully die, making them vulnerable to additional threats. A tree struggling with salt exposure allocates more of its energy to simply surviving the toxic conditions and less to maintaining its defenses against insects, diseases, and other stressors. Its bark might become thinner, more easily penetrated by boring beetles. Its immune responses might weaken, allowing fungal infections to take hold. During droughts, it has less capacity to close its stomata and conserve water because it's already struggling with water uptake due to the salt. The tree becomes compromised on multiple fronts simultaneously, each problem compounding the others. Drought can worsen ghost forest formation by reducing freshwater flushing, creating a paradox where too little rain accelerates the damage caused by too much salt water. In normal conditions, rainfall percolates through the soil, washing away some of the accumulated salt, diluting it, pushing it deeper into the ground or out toward the sea. This freshwater flushing provides temporary relief to stressed trees, giving them windows of recovery between salt intrusion events. But during extended droughts, this cleansing doesn't occur. The salt that arrives with each high tide or storm surge remains concentrated in the root zone. Without fresh water to dilute it, salinity levels climb higher and higher. Trees that might have survived with occasional freshwater relief instead find themselves in increasingly toxic soil. Coastal terrain is complex, making saltwater movement difficult to predict with precision. The coastline is not a simple, straight boundary. It's an intricate maze of inlets and outlets, high ground and low, sandy soils and clay soils, places where fresh water streams cut through toward the sea and places where the land rises into bluffs and ridges. Salt water doesn't flow uniformly across this varied landscape. It follows the paths of least resistance, seeking out low-lying areas, infiltrating porous soils more readily than dense clay. Two forests separated by just a few hundred yards might experience vastly different rates of salt intrusion depending on their elevation, their soil composition, their proximity to tidal channels. This complexity makes it challenging for scientists to predict exactly where ghost forests will form next or how quickly they'll expand. Human engineering can influence ghost forest vulnerability in some regions, sometimes protecting forests but often inadvertently making them more susceptible to damage. Ditches dug for mosquito control can provide channels for salt water to penetrate farther inland than it could naturally. Dams and water control structures can alter the flow of fresh water through coastal systems, changing the balance between fresh and salt. Roads built across wetlands can act as barriers, preventing natural water circulation and creating pockets where salt water accumulates. Conversely, levees and seawalls might protect some areas from storm surge, keeping salt water at bay, at least temporarily. But these structures are expensive to build and maintain, and they can't be placed everywhere. Often, they protect developed areas while leaving natural forests exposed. Tree rings show some forests were stressed by dredging and water changes decades ago, revealing that the vulnerability we see today has roots stretching back generations. Scientists can core into the trunks of both living and dead trees, extracting long, thin cylinders of wood that contain the entire growth history of the tree. Each ring represents 1 year of growth, and the width of that ring tells a story. Wide rings indicate years of abundant growth, when conditions were favorable. Narrow rings indicate stress, years when the tree struggled. By examining these patterns across many trees and comparing them with historical records of human activity, researchers have discovered that some coastal forests began showing signs of stress in the 1950s, 60s, and 70s, long before climate change became a household term. These earlier stresses, often caused by changes in water management or coastal development, may have left these forests more vulnerable to the additional pressures of rising seas and intensifying storms. Once saltwater intrusion begins, it can create feedback loops that speed up die-off, turning a manageable problem into an accelerating crisis. When some trees in a forest die, they stop drawing water from the soil. This water remains in the ground, and in coastal areas, it can lead to even higher water tables. Higher water tables mean roots spend more time submerged, experiencing both waterlogging and increased exposure to whatever salt is present. Additionally, when trees die, the forest canopy opens up. More sunlight reaches the ground, changing the microclimate. Different plants begin to grow, species adapted to wetland conditions rather than forest conditions. These new plants further alter the hydrology and soil chemistry. Each change triggers additional changes, and the system tips progressively farther from its original forested state toward a new equilibrium as wetland or open water. Forest edges closest to the coast typically die first, creating an advancing front of mortality that moves gradually inland. If you were to visit a coastal forest experiencing saltwater intrusion year after year, you would notice this pattern clearly. The trees nearest the water's edge are already dead, gray skeletons standing in shallow water or marsh. Moving inland, you encounter trees that are clearly stressed but still alive, with sparse foliage and visible signs of decline. Farther still, the forest appears healthier, though careful observation might reveal subtle signs of the coming transformation. This gradient of damage reflects the gradient of salt exposure. The trees closest to the coast encounter salt water most frequently, in highest concentrations. As the sea continues to rise and storms continue to push surges inland, this front of mortality marches steadily forward, claiming more territory year by year. Some forests form unstable transition zones rather than collapsing instantly, existing in a state of limbo that might persist for years or even decades. These transition zones are fascinating and fragile places. The forest is clearly in decline, but it hasn't fully died. Some trees are dead, others are struggling, and a few might even appear reasonably healthy, at least to the casual observer. The understory vegetation is changing, with wetland plants increasingly common where forest herbs once dominated. The wildlife community is in flux, with species that depend on mature forest habitat disappearing while species adapted to wetlands and open areas moving in. These zones represent ecosystems in transformation, caught between what they were and what they're becoming. They're unstable because the trajectory is clear, but the timeline remains uncertain. Certain drought-tolerant trees may persist longer in mixed conditions, displaying unexpected resilience even as their neighbors succumb. Not all species respond identically to salt stress and waterlogging. Some trees, particularly those with deeper root systems that can access water below the salt-affected surface layers, or those with some inherent tolerance for water stress that gives them an advantage in dealing with the osmotic challenges of salty soil, manage to survive longer. These individuals become survivors in a dying forest, islands of life in a landscape of death. Eventually, if conditions continue to deteriorate, even these hardy individuals will fail. But in the meantime, they persist, and their persistence is valuable. It provides habitat for wildlife, stabilizes soil, and offers scientists clues about which genetic traits or physiological adaptations might help forests cope with changing conditions. Scientists sometimes call these longer-lasting transition zones zombie forests, a term that captures something essential about their nature. They're neither fully alive nor completely dead. They're forests that are dying but haven't finished dying, that continue to go through some of the motions of life even as their vitality drains away. The term might seem flippant, even disrespectful, but it communicates an important ecological truth. These forests are doomed. The processes underway are too far advanced to reverse without massive intervention, and often not even intervention can save them. But their demise is slow enough that they remain visible, present, functional in limited ways. They exist in a strange liminal space, and the term zombie forest acknowledges that strangeness, that sense of something that should have ended but continues to shamble forward. Where ghost forests are spreading. The transformation we've been exploring, this slow conversion of living forest into standing graveyards of dead trees, is not confined to a single location or a small patch of coastline. It is happening across vast stretches of the world's shores, and as our ability to detect and measure these changes improves, we're discovering that the phenomenon is far more widespread than anyone initially realized. Ghost forests are widespread on the U.S. mid-Atlantic coast, stretching along hundreds of miles of shoreline from Maryland down through the Carolinas. This region has become a kind of ground zero for ghost forest research in North America, partly because the changes here have been so dramatic and well documented, and partly because the landscape itself, with its low-lying coastal plains and extensive wetland systems, is particularly vulnerable to the effects of rising seas. Drive along certain coastal highways in this region and you'll see them yourself. Gray forests standing in shallow water on either side of the road, testimony visible to anyone who passes by. North Carolina's Down East region is one of the best-known hotspots, a place where ghost forests have become part of the local identity and landscape in profound ways. Down East refers to the coastal communities of Carteret County and surrounding areas, places with names like Cedar Island, Sea Level, and Atlantic. These are communities that have lived with the water for generations, where fishing and maritime traditions run deep. The forests here were once thick with pine and juniper, providing timber, wildlife habitat, and protection from storms. Now, vast areas have transitioned to ghost forest, the dead trees standing as markers of how dramatically the relationship between land and sea has shifted in just a few decades. Over 100,000 acres of U.S. coastal forest have transitioned since the late 1800s, a staggering figure that becomes even more sobering when you try to visualize what 100,000 acres actually means. That's more than 150 square miles, an area larger than many cities, transformed from living woodland into dead forest and marsh. This transition didn't happen all at once or at a steady rate. Instead, it's been episodic, accelerating during periods of particularly rapid sea level rise or following major storm events, then slowing during quieter periods, but always moving in the same direction, always claiming more territory for the sea. In North Carolina, more than 11,000 acres became ghost forest after Hurricane Irene alone, demonstrating how a single event can trigger transformations that might otherwise have taken years or decades to unfold. Before Irene made landfall in August 2011, many of these acres were already stressed, already showing signs of salt intrusion and decline. But the hurricane pushed them past the tipping point. The storm surge flooded these areas with salt water, depositing salt deep into the root zones of thousands upon thousands of trees. In the months and years that followed, scientists and residents watched as these forests died, the green fading from their canopies, the life draining from their trunks. 11,000 acres is a difficult number to truly comprehend until you've stood in one of these forests, surrounded by dead trees in every direction, realizing that what you can see is just a tiny fraction of the total area affected. One North Carolina refuge saw roughly half its land affected over 35 years, a transformation that unfolded across the span of a generation. When researchers first began studying this refuge in the early 1980s, it was predominantly forested wetland, thick with trees and rich with wildlife. By the mid-2010s, fully half of that forest had died, replaced by marsh grasses and open water. Scientists have documented this change through repeated aerial surveys, satellite imagery, and patient fieldwork, creating a detailed record of how the refuge transformed year by year. This kind of long-term documentation is invaluable because it allows us to understand not just that change is happening, but exactly how fast it's happening and what factors drive it forward or occasionally slow it down. A Virginia peninsula lost 41,300 acres, about 15% of its coastal land, between 2001 and 2014, a rate of loss that amounts to more than 3,000 acres per year. This peninsula, jutting out into the Chesapeake Bay and the Atlantic Ocean, has been particularly hard hit by the combined effects of sea level rise and land subsidence. The ground here is actually sinking even as the ocean rises, doubling the rate at which the relative water level increases. Forests that stood well above normal tides in the 1990s found themselves regularly flooded by the 2010s. The loss of 15% of the land area in just over a decade represents a dramatic reshaping of the landscape, one that has profound implications for the communities that call this peninsula home, for the wildlife that depends on these habitats, and for our understanding of how quickly coastal ecosystems can collapse under pressure. AI analysis has identified nearly 12 million dead trees along U.S. coasts, a number that would have been impossible to count using traditional survey methods. Artificial intelligence and machine learning have revolutionized our ability to detect and map ghost forests. By training computer algorithms to recognize the distinctive signatures of dead trees in satellite imagery and aerial photographs, researchers can now survey vast areas in a fraction of the time it would take to visit these sites on foot. The AI can distinguish between living trees with green canopies and dead trees with bare branches or sparse, brown foliage. It can work through thousands of square miles of imagery, identifying and counting individual dead trees with remarkable accuracy. 12 million trees represents an almost incomprehensible amount of death, a die-off so extensive that it's reshaping entire coastal ecosystems. Newer AI mapping suggests ghost forests may be expanding faster than older estimates indicated, a finding that has alarmed scientists and coastal managers alike. As the technology improves and more data becomes available, researchers have been able to refine their methods and extend their surveys to areas that were previously difficult to study. What they're finding is that ghost forests aren't just present in the well-known hotspots. They're appearing in places that weren't considered particularly vulnerable just a decade ago. The rate of expansion seems to be accelerating, likely driven by the accelerating rate of sea level rise itself, by the increasing frequency and intensity of coastal storms, and by feedback loops within the ecosystems themselves that speed the conversion from forest to wetland once it begins. Ghost forests also exist far beyond the United States, a reminder that this is a global phenomenon, not one confined to any single nation or region. Wherever there are coastal forests and rising seas, wherever salt water can intrude into areas that once held only fresh water, ghost forests can and do form. The specifics vary from place to place, influenced by local geology, climate, storm patterns, and human activities, but the fundamental process remains the same. Understanding ghost forests globally helps us see them not as isolated anomalies but as symptoms of planetary-scale changes in our climate and our coastlines. Canada has ghost forest remnants linked to the 1700 Cascadia earthquake, ancient ghost forests that tell a dramatic story of sudden coastal subsidence. On January 26, 1700, a massive earthquake struck the Pacific Northwest, generated by the rupture of the Cascadia subduction zone. The ground shook violently for several minutes, and when it was over, large stretches of coastline had dropped by several feet. Forests that had grown just above the high tide line suddenly found themselves below it, inundated by salt water with every tide. The trees died quickly, and their stumps and trunks, buried in the sediments that accumulated after the earthquake, remained preserved for centuries. Today, when these ancient ghost forests are exposed by erosion or discovered during archaeological excavations, they serve as powerful evidence of both the earthquake itself and the sudden, dramatic transformations that coastal landscapes can undergo. Europe's Wadden Sea region has similar coastal die-offs from storm surges, particularly along the coasts of the Netherlands, Germany, and Denmark. The Wadden Sea is a vast tidal flat system, constantly reshaped by the movement of tides and the power of storms. While this region has been heavily modified by human engineering, with extensive networks of dikes and drainage systems, there are still areas where forests meet the sea, and in these places, ghost forests have formed. Storm surges pushing across the North Sea can flood coastal forests with salt water, particularly during the severe winter storms that periodically batter this coast. The forests here might look different from those in North Carolina or Virginia, composed of different species adapted to different conditions, but the process of their death and the ghost forests they leave behind would be recognizable to anyone familiar with the phenomenon elsewhere. Australia has white ghost mangrove die-offs linked to cyclones and salt stress, a variation on the ghost forest theme that occurs in tropical and subtropical coastal systems. Mangroves are remarkable trees, specially adapted to live in salt water, their roots submerged at high tide, their leaves breathing in the salty air. They would seem immune to the processes that kill other coastal forests, and indeed, they're far more tolerant of salt and tidal flooding than most species. But they have their limits. Severe cyclones can damage or kill mangroves through physical destruction, tearing trees from their moorings or burying them in sediment. Extended droughts can stress mangroves by increasing soil salinity beyond even their considerable tolerance. When mangroves die in large numbers, they create white ghost forests, named for the distinctive pale gray color of their dead wood, which bleaches nearly white under the intense tropical sun. Bangladesh, Japan, and Scotland also have documented ghost forest-like zones, each with their own particular characteristics shaped by local conditions. Bangladesh, with its extensive river deltas and low-lying coastal areas, faces some of the world's most severe challenges from sea level rise. Ghost forests are forming as salt water penetrates farther up river channels and into coastal wetlands, killing trees that once thrived in brackish or fresh water conditions. Japan, an island nation ringed by thousands of miles of coastline and regularly struck by powerful typhoons and tsunamis, has areas where coastal forests have died from storm surge and seismic subsidence. Scotland, with its rugged coastlines and ancient peat bogs, has ghost forests of a different sort, preserved stumps and trunks of trees that grew thousands of years ago when sea levels were lower, now revealed as the peat erodes away and the sea reclaims land it once covered. The global distribution of ghost forests tells us something important. This is not a local problem with local solutions. It's a manifestation of changes happening to the entire planet, to the climate system that regulates temperature and rainfall, to the oceans that are absorbing heat and expanding, to the ice sheets that are melting and adding their water to the seas. Ghost forests are appearing on every inhabited continent, from the tropics to the temperate zones, in wealthy nations and poor ones, in densely populated areas and remote wilderness. They are one of the most visible signs of our changing world, markers written in dead wood that testify to the reality and the consequences of the changes we've set in motion. What happens to nature when a forest dies? When a forest dies and becomes a ghost forest, it doesn't simply vanish or remain frozen in time. Instead, it enters a new phase of existence, a period of transition and transformation that affects every aspect of the ecosystem, from the invisible microbes in the soil to the birds that once nested in the canopy, from the chemistry of the water flowing through it to the very air above it. Let us explore what happens in these spaces where death gives way to something new. As trees die, marsh plants often move in and replace the forest, taking advantage of the changed conditions that proved fatal to the trees. These marsh plants, grasses and sedges and rushes, are specialists in living at the boundary between land and water. They thrive in waterlogged, salty soils that would kill most upland species. Their roots are adapted to tolerate low oxygen conditions. Many can excrete salt through specialized glands on their leaves, a trick that allows them to drink salt water without poisoning themselves. As the dead trees stand gray and lifeless, these green plants spread across the forest floor, their roots knitting through the wet soil, their stems rising higher each year. Gradually, what was once the shaded understory of a forest becomes an open marsh, sunny and exposed, dominated by plants that grow in dense mats and sway in the wind that now blows freely through the spaces where tree trunks no longer obstruct it. Invasive reeds like phragmites can dominate these transition zones, and when they do, they fundamentally alter the character of the ecosystem. Phragmites, also known as common reed, is a tall, aggressive grass that forms dense, nearly impenetrable stands. It spreads rapidly through underground rhizomes that can extend many feet in a single growing season. Once established, phragmites crowds out native marsh plants, reducing the diversity of the plant community. These monocultures of tall reeds provide poor habitat for many native animals. Birds that feed on the seeds of diverse marsh plants find fewer food sources. Small mammals and reptiles that need open water or mudflats interspersed with vegetation find themselves shut out by the dense walls of reed stems. The transition from diverse forests to phragmites-dominated marsh represents not just a change in species but a significant loss of ecological complexity. Ghost forests disrupt carbon storage because forests hold large carbon reserves, accumulated over decades or centuries of growth. Every tree is essentially a storage vessel for carbon dioxide pulled from the atmosphere through photosynthesis. The carbon becomes part of the tree's structure, its trunk, branches, and roots, locked away for as long as the tree lives and even beyond, slowly released as the dead wood gradually decays. A mature forest contains enormous amounts of carbon, not just in the living trees but in the dead wood on the forest floor, in the organic rich soil, in the understory plants and root systems. This stored carbon represents decades or centuries of atmospheric carbon dioxide converted into solid form and sequestered away from the atmosphere where it would contribute to warming the planet. When forests die, some of that stored carbon can be released, returned to the atmosphere as the dead trees decay. The process isn't instantaneous. A dead tree standing in a marsh might persist for years or even decades before it falls and begins to rot in earnest. But eventually, fungi and bacteria break down the wood, respiring carbon dioxide as they do so. The carbon that the tree spent decades accumulating is released back into the atmosphere over a much shorter period as decay progresses. Some of the carbon becomes incorporated into the marsh soil, where it may remain sequestered. But much of it, particularly from the above-ground parts of the trees, returns to the air. This release contributes to the very climate change that caused the forest to die in the first place, creating another feedback loop that accelerates warming. New marshes may store less carbon than the forests they replace, though the picture is complex and scientists are still working to fully understand the carbon dynamics of these transitioning systems. Marshes do store carbon, particularly in their waterlogged soils where decomposition is slow due to low oxygen availability. Salt marshes, in particular, can be remarkably efficient at sequestering carbon in their sediments over long time scales. But the total amount of carbon stored in a marsh is often less than what was stored in the forest it replaced, simply because marshes lack the massive, long-lived woody structures that trees provide. The transition from forest to marsh can represent a net loss of carbon storage capacity, at least in the short to medium term, contributing to atmospheric carbon dioxide levels and climate warming. LiDAR mapping can measure biomass loss and has shown major carbon declines in these transitions, providing scientists with precise, quantitative data about how much carbon is being lost as forests die. LiDAR, which stands for light detection and ranging, uses laser pulses to create detailed three-dimensional maps of the landscape, including the height and density of vegetation. By comparing LiDAR surveys taken years apart, researchers can measure exactly how much biomass, and therefore how much carbon, has disappeared from an area. In some ghost forest zones, these measurements have revealed losses of hundreds of tons of carbon per acre, massive amounts that represent significant contributions to atmospheric carbon dioxide when multiplied across the thousands of acres of forest that have died. Root decay can release sulfitic acids that alter nearby water chemistry in ways that ripple through the ecosystem. When roots die and decay in waterlogged, low-oxygen environments, sulfur compounds in the soil undergo chemical transformations. Bacteria that thrive in these anaerobic conditions reduce sulfate to sulfide, which can then combine with other elements to form various sulfur compounds. When these areas are exposed to air, either through water level fluctuations or disturbance, the sulfides can oxidize, producing sulfuric acid. This acid can dramatically lower the pH of water draining from ghost forest areas, making streams and creeks more acidic than they would naturally be. Streams near ghost forests can become more acidic and disrupt fish migration, creating barriers to species that depend on moving between different habitats to complete their life cycles. Many fish species, including various herrings, shads, and other anadromous fish that spawn in freshwater but live most of their lives in the ocean, are sensitive to changes in water chemistry. They navigate by chemical cues, following gradients of salinity and pH to find their way to spawning grounds. When streams become unusually acidic due to sulfitic runoff from ghost forests, these cues can be disrupted. Fish may avoid entering these streams, or if they do enter, they may experience physiological stress that reduces their survival or reproductive success. The death of a forest can thus affect creatures that never lived in the forest itself, demonstrating how interconnected ecosystems truly are. Ghost forest roots can leach phosphorus into bays, adding nutrients to coastal waters in concentrations that can overwhelm the natural balance. Phosphorus is an essential nutrient for plant growth, but like many things in nature, it causes problems when present in excessive amounts. Tree roots accumulate phosphorus from the soil during the tree's lifetime. When the roots die and begin to decay, this phosphorus is released into the surrounding water. In areas with extensive ghost forests, the total amount of phosphorus leaching from millions of decaying root systems can be substantial, flowing into creeks and rivers and eventually into estuaries and bays. This nutrient release can fuel algal blooms that harm shellfish beds, creating cascading effects through the coastal food web. Algae, like all plants, need nutrients to grow, and phosphorus is often one of the limiting factors that keeps algal populations in check. When excess phosphorus becomes available, algae can reproduce rapidly, forming blooms that turn the water green or brown. These blooms can be harmful in several ways. Some species of algae produce toxins that poison fish and shellfish. Even non-toxic blooms cause problems when they die and decompose, because the bacteria that break down the dead algae consume oxygen, creating low oxygen zones where shellfish and other bottom-dwelling organisms suffocate. Shellfish beds that once produced abundant oysters, clams, and scallops can be devastated by these oxygen-depleted conditions. Another way that the death of a forest affects species and ecosystems that might seem far removed from the trees themselves. Yet amid all this disruption and loss, ghost forests also create new opportunities, new niches, new habitats that some species are quick to exploit. Fallen trunks can trap sediment and help build new resilient transition zones, functioning almost like natural dams or levees. When a dead tree finally falls, it doesn't immediately disappear. The trunk might lie partially submerged in marsh water for years, slowly decaying. As water flows around and over this obstacle, it slows down, and when water slows, sediment settles. Over time, sediment accumulates around the fallen trunk, building up the marsh surface, creating slightly higher ground where other plants can establish. These small elevational differences matter enormously in marshes, where a few inches can determine whether a spot is submerged at high tide or remains above water. The fallen trees of ghost forests thus contribute to building the marshes that replace them, their decay supporting new growth. Dead trees can slow marsh grass spread by creating shaded microclimates where conditions remain different from the open marsh. A standing dead tree, even without leaves, casts some shadow. The trunk itself blocks sun, and the branches, though bare, create patterns of light and shade that shift throughout the day. In these shaded spots, the soil stays slightly cooler and retains moisture longer. Some plant species that couldn't survive in full sun can persist in these refugia. The diversity of the marsh is maintained at a slightly higher level than it would be if the trees weren't present. This is temporary, of course. Eventually the trees will fall and the shade will disappear. But in the years or decades it takes for that to happen, they provide valuable habitat complexity. Burrowing crabs thrive in exposed roots and help aerate soil, playing an important role in maintaining marsh health. Fiddler crabs and other species dig extensive burrow systems in marsh sediments, and they particularly favor the areas around dead tree roots where the combination of stable structure and decaying organic matter creates ideal conditions. These burrows serve as shelter for the crabs, protecting them from predators and providing refuge during extreme tides. But the burrows also benefit the marsh ecosystem more broadly. Each burrow is a tube through which air can penetrate into otherwise oxygen-poor sediments. This aeration supports different types of bacteria and changes the chemistry of the soil in ways that can benefit marsh plants. The crabs also consume detritus and help break down organic matter, accelerating the nutrient cycling that supports the marsh ecosystem. Fungi colonize dead trunks quickly, supporting specialized insects, and these insects in turn support birds and other predators. Within months of a tree's death, fungi begin to infiltrate the wood. You can see their fruiting bodies, mushrooms and shelf fungi, emerging from the bark. Inside the trunk, fungal hyphae spread through the wood, breaking it down, softening it. This fungal-infected wood becomes habitat for a host of specialized insects. Beetles bore into the decaying wood, their larvae developing inside galleries they excavate. Moths and flies lay eggs in the soft, rotting wood. Each species has its own requirements, its own preferred stage of decay. Some arrive when the wood is newly dead and still relatively hard. Others come later, when the wood is softened further. Together, these insects form a complex community, and they become food for woodpeckers, warblers, and other insectivorous birds that forage on dead trees. Rare plants like orchids can cling to shaded ghost trunks in humid decay zones, finding niches that wouldn't exist in either intact forest or open marsh. Some orchid species are epiphytes, plants that grow on other plants rather than rooting in soil. They need high humidity, filtered light, and a stable surface to attach to. The trunks of dead trees, particularly in the humid environment of coastal marshes, can provide exactly these conditions. Mosses and lichens colonize the bark, creating a thin layer of organic matter that orchid seeds can germinate in. The orchid's roots cling to the bark, absorbing water and nutrients from rain and from the decomposing wood beneath them. These orchids might be rare in the broader landscape, but in ghost forests they can find temporary homes, adding an unexpected element of beauty and diversity to these spaces between forest and marsh. Ghost forests can briefly become unusual biodiversity hotspots before full marsh takeover, concentrating species from multiple habitats in a single location. In the early stages of transition, before the standing dead trees have all fallen and before marsh plants have completely carpeted the ground, ghost forests contain elements of 3 different habitat types simultaneously. There are the remnants of the forest, the dead trees and the soil structure and some of the understory plants. There are the emerging marsh elements, the salt-tolerant grasses and the water pooling on the surface. And there are the unique features of the ghost forest itself, the standing dead wood and the particular combination of light, water, and decay. Species associated with all 3 habitat types can be present at once. Forest birds might still visit to forage on insects in the dead wood. Marsh birds arrive to hunt in the pools and grasses. Species that specialize in edge habitats or disturbed areas thrive in the complexity. It's a temporary phenomenon, lasting only until the transition completes and the marsh fully establishes, but while it lasts, these in-between spaces can support remarkable diversity. How wildlife uses the dead trees. In the midst of all this death and transformation, life finds opportunities. The standing dead trees of ghost forests, stripped of their leaves and slowly decaying, might seem barren and lifeless at first glance. But look more closely, watch more patiently, and you'll discover that these gray sentinels serve new purposes, support new communities, and provide resources that wouldn't exist in either a living forest or a fully developed marsh. Standing dead trees can provide perches for ospreys, those magnificent fish-hunting raptors that patrol coastal waters with keen eyes and powerful talons. Ospreys are particular about their perches. They need clear sight lines to the water below, unobstructed views that allow them to spot fish swimming near the surface. They need sturdy branches capable of supporting their weight as they scan the water and launch into their spectacular hunting dives. Living forests, with their dense canopies and layers of foliage, don't provide ideal osprey habitat. The leaves block the view, the branches are hidden within the canopy, and the forest floor is too far from open water. But ghost forests, with their tall, bare trunks rising from marsh and shallow water, are perfect. The trees stand isolated or in small groups, their branches naked and strong, offering commanding views across the wetland. An osprey can perch on these dead limbs, surveying its hunting grounds, waiting for the right moment to dive. Bald eagles also use ghost forest snags for hunting and lookout points, and for the same reasons that ospreys favor them. Eagles are larger and heavier than ospreys, requiring even more substantial perches. The thick main branches of dead trees, stripped of smaller twigs and foliage, provide exactly what eagles need. From these elevated positions, eagles can watch for fish in the channels and pools below, but they also scan for other prey, waterfowl swimming in the marsh, small mammals moving through the grass, even carrion washed up along the water's edge. The ghost forest becomes a hunting ground, and the dead trees serve as the eagles' watchtowers. In some ghost forest areas, you can observe multiple eagles and ospreys, each occupying its preferred perch, coexisting in this liminal landscape that serves both species better than the living forest ever did. Some raptor populations may increase in marsh transition landscapes, a phenomenon that scientists have documented through careful population surveys and nest monitoring. Before the forest died, these areas might have supported a few raptors, birds that hunted along the forest edges where woodland met water. But the transition from forest to ghost forest to emerging marsh can actually increase the total raptor population, at least temporarily, because the landscape now offers both the perching and nesting opportunities of the dead trees and the abundant prey of the developing marsh ecosystem. The marsh teems with small fish, frogs, snakes, rodents, and birds, all potential prey for hunting raptors. The combination of abundant food and excellent hunting perches creates ideal conditions, and raptor numbers rise accordingly. This is one of the paradoxes of ghost forests. They represent ecological loss in one sense, the death of a forest ecosystem, but they can simultaneously create conditions that benefit certain species, at least for a time. Dead trunks create habitat for insects that may not thrive in living forests, opening niches for specialists that depend on dead and decaying wood. Living trees have defenses against insects, thick bark, toxic sap, immune responses that can isolate and kill invading larvae. But dead trees have no such defenses. They're open to colonization, and countless insect species have evolved to take advantage of this resource. Wood-boring beetles tunnel through the sapwood and heartwood, their larvae spending months or years developing inside the trunk. Carpenter ants excavate galleries in the softening wood, creating vast interconnected chambers where their colonies thrive. Termites, in warmer regions, consume the dead wood from the inside out, reducing solid timber to a hollow shell filled with their mud tunnels, Each of these insects plays a role in breaking down the dead tree, hastening its return to soil and nutrients, while simultaneously serving as food for the birds and other predators that hunt them. Some ghost zones develop unique niches not found in healthy woodland, combinations of conditions that create opportunities for unexpected species and communities. A living forest is shaded, relatively dry in its interior, structured in predictable ways with a canopy layer, an understory, and a forest floor. A fully developed marsh is open, wet, dominated by grasses and sedges. But a ghost forest is neither and both. It has the vertical structure of trees, but without the shade of a closed canopy. It has standing water like a marsh, but also the woody debris and complex root systems of a forest. It's sunny in some spots and shaded in others. It's wet but with dry microhabitats on fallen logs and standing stumps. This heterogeneity, this patchwork of different conditions existing side by side, creates niches that don't exist in more homogeneous habitats. Species that need just the right combination of sun and shade, wet and dry, wood and water can find exactly what they need in these transitional spaces. Epiphytic bromeliads can invade bark crevices and form aerial gardens, particularly in warmer coastal regions where these tropical and subtropical plants naturally occur. Bromeliads are fascinating plants, many of which don't root in soil at all but instead perch on tree branches and trunks, their roots serving mainly to anchor them in place. They collect water in the rosettes formed by their overlapping leaves, creating tiny pools suspended in the air. In living forests, bromeliads compete for space on tree branches, limited by the density of the canopy and the vigor of the living trees, which can shed branches colonized by too many epiphytes. But on dead trees, there's no such competition. The trees aren't shedding branches anymore. The bark crevices and branch angles remain stable for years. Bromeliads can colonize extensively, turning the dead trunks into vertical gardens, dozens or even hundreds of plants clustered on a single tree, their green rosettes creating splashes of color against the gray wood. Those bromeliads can host unique ant colonies, reshaping microecosystems in remarkable ways. The water-filled centers of bromeliad rosettes become tiny aquatic habitats, home to mosquito larvae, small crustaceans, and other invertebrates. But some ant species have evolved to live in these aerial pools as well. They build their nests among the bromeliad leaves, their colonies living entirely above the ground, sustained by the insects they hunt and the detritus that collects in the plant's water reservoirs. These ants, in turn, affect the bromeliad. They may defend it from herbivores, attacking any insect that tries to feed on the plant's leaves. They contribute nitrogen to the plant through their waste, fertilizing their host. The relationship between ant and plant can become so specialized that certain ant species live only in certain bromeliad species, and vice versa. When these partnerships establish themselves on ghost forest trees, they create ecosystems within ecosystems, complex communities existing on individual dead trunks, each tree becoming a world unto itself. The wildlife that uses ghost forests reminds us that ecosystems are always more complex than they first appear. What looks like simple death and decay is actually a transformation, an opening of new possibilities. The ospreys and eagles perching on dead branches, the beetles burrowing through dead wood, the bromeliads colonizing dead bark, all of these represent life taking advantage of change, species finding opportunities in altered landscapes. Nature is resilient and adaptive, constantly reshaping itself, finding ways to persist and even thrive in the face of transformation. The invisible gas in chemistry. Beneath the visible transformations of ghost forests, beneath the dying trees and spreading marsh grasses, beneath the hunting eagles and burrowing crabs, there exists another layer of change, invisible to our eyes but profound in its implications. This is the realm of chemistry and microbiology, of gases rising from wet soil, of bacteria transforming compounds in ways that ripple outward to affect the entire planet's climate. Waterlogged soils encourage anaerobic bacteria, microorganisms that thrive in environments without oxygen. When soil becomes saturated with water, the spaces between soil particles that would normally hold air become filled with liquid instead. Oxygen, which dissolves poorly in water, becomes scarce. Most familiar soil bacteria need oxygen to survive, just as we do. But anaerobic bacteria are different. They've evolved to function without oxygen, using alternative chemical pathways to break down organic matter and obtain energy. In the waterlogged soils of ghost forests and emerging marshes, these anaerobic bacteria flourish, their populations exploding as conditions become increasingly favorable for their particular way of life. Anaerobic bacteria can produce nitrous oxide, a powerful greenhouse gas that most people have never heard of, though its impact on our climate is substantial. These bacteria obtain energy by breaking down nitrogen compounds in the soil, and nitrous oxide is one of the byproducts of this process. The gas bubbles up through the waterlogged soil and escapes into the atmosphere, invisible and odorless, undetectable without specialized equipment. In small amounts, this is a natural part of the nitrogen cycle, occurring in wetlands and waterlogged soils throughout the world. But when vast areas of coastal forest transition to wetland conditions all at once, when thousands of acres of previously well-drained forest soil become permanently saturated, the total amount of nitrous oxide being produced and released can increase dramatically. Nitrous oxide is around 300 times more potent than carbon dioxide as a greenhouse gas, meaning that molecule for molecule, it traps far more heat in the atmosphere. A single ton of nitrous oxide released into the air has the same warming effect as 300 tons of carbon dioxide. This makes it one of the most powerful greenhouse gases we need to be concerned about, even though it's present in the atmosphere at much lower concentrations than carbon dioxide. The nitrous oxide rising from ghost forest soils might be invisible, might seem insignificant compared to the dramatic visual changes of dying trees, but its contribution to climate warming is very real and very significant. Dead tree stems can act as chimneys for methane and carbon dioxide emissions, providing pathways for these gases to escape from the soil and reach the atmosphere far more efficiently than they could through soil alone. When a tree dies but remains standing, its internal structure begins to change. The wood starts to decay, creating hollow spaces and channels. The boundary between the tree's interior and the waterlogged soil around its roots becomes porous. Gases produced by bacteria in the soil can enter the tree's root system and travel upward through the trunk, following the same pathways that once carried water and nutrients when the tree was alive. These gases emerge from cracks in the bark, from broken branches, from the top of the trunk, released into the air many feet above the ground. This elevated release point means the gases bypass the surface layers of soil and water where some of them might otherwise be consumed by other bacteria or dissolved. In some reservoirs and wetlands, Dead stems may contribute up to 15% of total gas flux, a surprisingly large proportion that scientists didn't fully appreciate until recently. Researchers have measured gas emissions from dead trees by fitting them with specialized chambers that capture the gases emerging from the bark and quantify how much is being released. What they've found is that while each individual tree might not seem to emit very much, when you multiply that emission rate by the thousands or millions of dead trees standing in ghost forests across a region, the total contribution becomes substantial. These tree stem emissions can represent a significant fraction of all the greenhouse gases escaping from these transitional ecosystems, comparable in some cases to the emissions from the open water and marsh surfaces themselves. Eddy covariance towers measure turbulent gas exchange in ghost forest zones, providing scientists with continuous, high-resolution data about the invisible flows of carbon and other gases moving between the ecosystem and the atmosphere. These towers stand tall above the landscape, bristling with sensitive instruments that measure wind speed and direction, temperature and humidity, and most importantly, the concentrations of various gases in the air. The instruments work by detecting tiny, rapid fluctuations in these parameters, fluctuations caused by turbulent eddies in the air that mix gases from the surface upward into the atmosphere. By analyzing these fluctuations mathematically, scientists can calculate the net flux of gases, determining whether the ecosystem is, on balance, absorbing carbon dioxide from the atmosphere or releasing it, and how much methane and other gases are escaping. Some studies suggest ghost forest canopies can leak more methane than open marsh, a finding that initially surprised researchers. The conventional wisdom had been that open water and marsh surfaces were the primary sources of methane in coastal wetlands, with the gas bubbling up from anaerobic sediments. And indeed, these surfaces do release substantial methane. But the dead trees add another dimension to the story. The tree stems act as those chimneys we discussed, providing efficient pathways for methane to escape. Additionally, the partially decayed wood itself can host methane-producing bacteria in its waterlogged interior. The combination of these factors means that areas with standing dead trees can, in some cases, release more methane than adjacent areas of open marsh without trees, even though the fundamental source of the methane, the anaerobic bacteria in waterlogged soil, is similar in both places. Yet even in this story of greenhouse gas emissions, there are nuances and complexities that prevent simple conclusions. Microbes living on dead trees may convert methane into less harmful gases, providing a partial offset to the emissions. Certain bacteria, called methanotrophs, consume methane as their energy source, oxidizing it to carbon dioxide. Now, carbon dioxide is itself a greenhouse gas, so this conversion doesn't eliminate the climate impact entirely. But remember, methane is a far more potent greenhouse gas than carbon dioxide, roughly 25 to 30 times more powerful over a century-long timescale. So converting methane to carbon dioxide actually reduces the total warming effect. These methanotrophic bacteria colonize the surfaces of dead trees, particularly in the bark crevices and in the partially decayed wood where moisture remains high. As methane travels up through the tree stem toward the atmosphere, some of it encounters these bacteria and gets converted before it can escape. The efficiency of this conversion varies depending on conditions, temperature, moisture, the specific communities of bacteria present, but it represents a natural mechanism that moderates the methane emissions from these systems. The invisible chemistry of ghost forests reminds us that ecosystems function on multiple levels simultaneously. We see the dead trees, the spreading marsh, the hunting birds. We might not see the bacteria in the soil, the gases rising through hollow tree trunks, the chemical transformations occurring in the boundary between wood and water. But these invisible processes are just as real and just as important as the visible ones. They connect local ecosystems to global climate patterns, linking the death of a forest on one stretch of coast to atmospheric changes that affect the entire planet. The greenhouse gases rising from ghost forests contribute to the same climate warming that's causing sea levels to rise. That's creating more ghost forests that will produce more greenhouse gas emissions in a self-reinforcing cycle. It's another feedback loop, another way that changes in one part of the Earth system amplify changes elsewhere. Breaking these cycles, slowing these processes, requires understanding them in all their complexity, seeing both the visible transformations and the invisible flows of elements and energy that accompany them. How scientists track ghost forests. Understanding ghost forests requires more than simply visiting them and observing what's visible to the naked eye. It requires tracking changes across vast areas over long periods of time, detecting subtle signs of stress before they become obvious, and carefully measuring the environmental conditions that drive forest death. Scientists have developed an impressive array of tools and techniques to study these transforming landscapes, combining cutting-edge technology with patient fieldwork to build a comprehensive picture of how, where, and why ghost forests form. Scientists track ghost forests using satellite imagery across decades, creating time-lapse records of coastal change that no single human observer could compile through ground-based observation alone. Satellites orbiting hundreds of miles above Earth capture images of the surface repeatedly, day after day, year after year, building vast archives of data that document how our planet's landscapes transform over time. For studying ghost forests, these satellite images are invaluable because they provide consistent, objective records of coastal forests across regions far too large to survey on foot or even by aircraft. A single satellite image might cover thousands of square miles, capturing entire coastlines in a single frame, allowing scientists to see patterns and trends that would be invisible at smaller scales. Landsat imagery dating back to 1984 is commonly used for long-term change detection, providing over 40 years of continuous coverage that spans the period during which many of today's ghost forests first began to form. The Landsat program, a joint effort of NASA and the U.S. Geological Survey, has been continuously capturing images of Earth's surface since 1972, though the 1984 start date reflects when the image quality and consistency became reliable enough for detailed vegetation studies. These images aren't photographs in the traditional sense. Instead, they're digital data capturing reflected light in multiple wavelengths, including some outside the range of human vision. Healthy vegetation has a distinctive signature in these images, reflecting strongly in near-infrared wavelengths while absorbing visible light for photosynthesis. Dead or stressed vegetation has a different signature, reflecting less near-infrared and more visible light. By comparing images from different years, scientists can identify where healthy forest has transitioned to stressed or dead forest, tracking the expansion of ghost forest zones year by year. Google Earth helps validate visible changes over time, providing a more accessible and visual way to explore how specific locations have transformed. While Landsat and other research satellites provide the data scientists need for rigorous analysis, Google Earth compiles high-resolution imagery from multiple sources into an interface that anyone can use. Researchers studying ghost forests can use Google Earth to zoom in on specific sites, switching between images captured in different years to watch the transformation unfold. They can identify the year when a particular forest patch first showed signs of widespread death, or track how quickly dead trees fall and disappear after dying. They can share these visual records with colleagues, with students, with the public, making the reality of ghost forest expansion tangible and undeniable. The ability to see a vibrant green forest in a 2005 image and then switch to a 2015 image showing the same location gray and lifeless is powerful in a way that graphs and statistics sometimes aren't. Machine learning can detect dead trees by pale bark and branch shadows, automating the process of identifying and counting individual trees across vast areas. Training a computer algorithm to recognize dead trees in aerial imagery requires first showing it thousands or tens of thousands of examples, images where human experts have already identified which trees are dead and which are alive. The algorithm learns to recognize the visual patterns associated with each category: the pale, reflective bark of dead trees versus the darker bark of living ones, the stark shadows cast by bare branches versus the softer, diffuse shadows under leafy canopies, the texture and color differences between dead and living forest. Once trained, the algorithm can process new images, identifying dead trees automatically with accuracy that often rivals or exceeds human observers. This automation is crucial because the scale of ghost forest expansion is simply too large for humans to map manually. There are millions of trees to identify across thousands of square miles of coastline. AI trained on aerial images has detected over 11 million dead trees from Maine to South Carolina, a monumental achievement that has transformed our understanding of ghost forest extent. This number represents countless hours of computation, algorithms working through vast libraries of aerial imagery, identifying and tallying dead trees one by one across the entire U.S. Atlantic coast. 11 million is an almost incomprehensible number, far more than anyone could count in a lifetime of fieldwork. The AI doesn't just count trees, it also maps their locations, creating detailed datasets that show exactly where ghost forests have formed, how dense they are, how they're distributed across the landscape. Scientists can use these maps to identify patterns, to correlate ghost forest locations with other environmental variables like elevation, distance from the coast, soil type, or storm history. The insights gained from this AI-enabled mapping have reshaped scientific understanding of how widespread and significant ghost forests truly are. Hyperspectral drones can detect stress chemicals in trees before they visibly gray, providing an early warning system that can identify forests at risk before the damage becomes irreversible. Hyperspectral sensors are sophisticated instruments that measure reflected light across dozens or even hundreds of narrow wavelength bands, far more than the 3 or 4 bands captured by standard cameras or even most satellite sensors. This detailed spectral information reveals subtle changes in the chemical composition of leaves and bark. When trees are stressed by salt exposure, they produce specific stress compounds, and the concentrations of various pigments and other chemicals in their tissues change in measurable ways. These chemical changes alter the tree's spectral signature, the precise pattern of wavelengths it reflects and absorbs. Hyperspectral sensors can detect these changes even when the tree still looks healthy to the human eye, still has green leaves, still appears to be thriving. By mounting these sensors on drones that can fly low over forests, covering areas too small for satellites but too large for easy ground surveys, researchers can map forest stress at high resolution, identifying vulnerable areas and tracking how stress progresses over time. Field teams confirm causes by testing salinity and sulfides in soil and water, because while remote sensing can tell us where trees are dying, it can't definitively tell us why without ground truthing. Scientists wade into ghost forests carrying bottles for water samples, soil cores to extract sediment from various depths, and portable instruments to measure pH, salinity, and other parameters on site. They measure how salty the soil is around tree roots, comparing living trees to recently dead ones to stressed ones that are still hanging on. They test water in nearby creeks and pools for sulfides and other chemical indicators of the processes we discussed earlier. They note the species of dead trees, the presence or absence of specific signs of stress or disease, the height above sea level, the frequency of tidal flooding. All of this field data complements the satellite and drone imagery, providing the context and detail needed to understand not just that forests are dying, but exactly why they're dying in each specific location. Controlled flooding experiments simulate hurricane conditions to study early ghost stages, allowing scientists to observe and measure the processes of forest decline under controlled conditions where they can monitor every variable. In these experiments, researchers might build enclosures around groups of trees, small sections of forest that can be flooded with salt water at specific concentrations and for specific durations, mimicking what happens during storm surge events. They measure how trees respond, how quickly salt accumulates in leaves and stems, how photosynthesis rates change, how root function is affected, when visible symptoms of damage first appear. They sacrifice some trees at intervals, carefully dissecting them to examine internal changes, measuring stress hormones and defensive compounds, documenting the progression of damage at the cellular level. These experiments are challenging to conduct and limited in scale, but they provide insights that can't be gained any other way, revealing the mechanisms and timelines of salt-induced tree death in detail that would be impossible to capture in natural settings where countless variables all change simultaneously. The combination of all these approaches, satellite monitoring and AI analysis, drone surveys and field sampling, controlled experiments and long-term observation, gives scientists an increasingly complete picture of ghost forests. They can detect where forests are dying, how fast the death is spreading, what's causing it, how ecosystems respond, and what might happen next. This knowledge is essential for understanding one of the most visible manifestations of climate change and sea level rise, and for helping coastal communities and ecosystems prepare for a future where ghost forests will likely become even more common. People, money, and coastal life. Ghost forests are not just environmental phenomena, not just matters of scientific interest or ecological concern. They are events that touch human lives in immediate and profound ways, reshaping communities, altering economies, and forcing people to reckon with losses both tangible and intangible. The death of coastal forests reverberates through the human world, affecting livelihoods and property values, traditions and futures. Ghost forests affect tourism because scenic forest trails disappear, and with them go the experiences that drew visitors to these coastal areas in the first place. People travel to coastal regions for many reasons, but among them is the desire to walk through beautiful forests, to hike beneath canopies of green, to experience the quiet peace of woodland paths winding through diverse ecosystems. When those forests die, when the trails that once passed through shade and shelter now traverse gray landscapes of standing dead trees and spreading marsh, the appeal diminishes. The experience becomes less about beauty and tranquility and more about witnessing loss and change. Some visitors are drawn to that, curious about ghost forests or concerned about climate change and wanting to see its effects firsthand. But for every visitor intrigued by the strangeness of ghost forests, there are others who simply choose to vacation elsewhere, seeking the intact natural beauty they remember or imagined. Some regions report forest trail losses of about 20% due to ghost forest expansion, a substantial reduction in the recreational infrastructure that supports outdoor tourism. 1 in 5 trails no longer usable, no longer offering the experiences they were designed to provide. These aren't just statistics. Each closed or degraded trail represents investments made in trail construction and maintenance, maps and guidebooks that became outdated, established hiking routes that can no longer be recommended. For the communities that depend on hiking and nature tourism, losing 20% of their trail network is a significant economic blow, reducing their ability to attract and accommodate visitors who come specifically for outdoor recreation. Tourism losses in parts of North Carolina have been estimated at $2 to $5 million per year, real money flowing out of local economies, money that once supported restaurants and hotels, guide services and outdoor equipment shops, gas stations and grocery stores. In small coastal communities, losses of this magnitude can be devastating. These aren't wealthy resort towns with diverse economic bases. They're often modest communities where tourism provides crucial income, where the difference between $2 million and $5 million in annual visitor spending can mean the difference between businesses staying open or closing, between young people finding local jobs or having to move away. The economic ripples spread far beyond the tourism industry itself, affecting tax revenues that support schools and infrastructure, property values, and the overall viability of these communities as places where people can make a living. Kayaking tours sometimes pivot to ghost narrative themes to stay relevant, adapting their offerings to acknowledge and interpret the changing landscape rather than pretending it hasn't changed. Tour operators who once marketed their excursions as paddle through pristine coastal forests now offer witness climate change firsthand or explore the haunting beauty of ghost forests. The experience they provide is fundamentally different, less about escapism and more about education and awareness, less about pristine nature and more about nature in transition. Some tourists appreciate this shift, valuing the opportunity to learn about environmental change in a direct, visceral way. The guides tell stories about what the forests once looked like, explain the science behind their death, point out the wildlife that has adapted to the new conditions. It's a form of ecological interpretation, turning the tours into outdoor classrooms. But it's also an acknowledgement of loss, acceptance that the old experience is gone and won't return, and that survival requires adapting to new realities. Waterfront homes near ghost zones may sell at 10 to 25% discounts compared to similar properties in areas with intact forests, a significant financial impact for homeowners who thought of their properties as secure investments. Imagine purchasing a home with a beautiful view of coastal forest, paying a premium for that natural setting, planning to live there for years or even retire there. Now imagine watching that forest die over the course of a few years, the view from your windows transforming from green vitality to gray desolation. When you try to sell, potential buyers see the ghost forest and understand what it implies: rising water, increasing flood risk, a landscape in decline. They offer less, sometimes substantially less, than comparable homes in more stable areas. For some homeowners, particularly those who are already near the financial edge, this loss of property value can be catastrophic. It can trap them in places that are becoming increasingly risky to live, unable to sell and move without taking losses they can't afford. Insurance premiums have risen in some ghost-adjacent areas, pricing people out, creating another financial pressure that compounds the property value losses. Insurance companies are businesses that assess risk, and ghost forests are visible signals of increasing flood risk, of land subsiding or sea level rising, of coastal areas becoming more vulnerable to storm damage. When insurers see ghost forests spreading, they respond by raising premiums, sometimes dramatically, or by refusing to offer flood insurance at all in the most vulnerable areas. For homeowners, this can mean annual insurance costs that double or triple, climbing from manageable expenses to burdens that consume significant portions of household budgets. Some people can't afford the new premiums and choose to go without insurance, gambling that they won't experience a catastrophic flood. Others find that they can no longer afford to live in their homes at all once insurance costs are factored in, and they're forced to sell and move, often at the discounted prices we just discussed, accepting financial losses as the price of escaping an increasingly untenable situation. Agriculture can collapse in coastal areas when saltwater intrusion ruins cropland, destroying livelihoods that may have sustained families for generations. Farming in coastal areas has always involved managing the relationship between fresh water and salt water, but farmers developed practices over decades or centuries that worked as long as conditions remained relatively stable. They knew which fields could be planted and which were too wet, which crops could tolerate occasional brackish flooding and which needed to be kept high and dry. But as sea levels rise and storm surges push deeper inland, the old rules stop working. Salt water reaches fields that were always safe before. The soil salinity creeps upward year by year until crops that once thrived begin to fail. Yields decline, then collapse entirely. Some farmers try to adapt, switching to more salt-tolerant crops, installing drainage systems or building berms to keep salt water out. But these adaptations are expensive and don't always work, especially when the rate of change accelerates. Some families who have farmed the same land for 3 or 4 or 5 generations watch helplessly as that land becomes unfarmable, as their heritage and livelihood drain away with the rising salt water. They may try to sell, but who wants to buy farmland that can no longer support crops? Many are forced to abandon agriculture entirely, seeking other work, leaving the land to transform into marsh or ghost forest, another casualty of the changing coast. These human impacts of ghost forests are sometimes harder to quantify than the ecological ones, harder to measure in the neat terms that scientists prefer. But they're no less real. Behind every statistic about declining property values or lost tourism revenue or abandoned farmland, there are people experiencing loss and disruption, families making difficult choices, communities watching their ways of life change in fundamental ways. The gray standing trees are witnesses not just to ecological transformation but to human stories of adaptation and resilience, of financial hardship and difficult departures, of grief for what's been lost and uncertainty about what comes next. Culture, identity, and community loss. Beyond economics and ecology, beyond property values and tourism dollars, ghost forests touch something deeper in the human experience. They affect our sense of place, our connection to history, our understanding of who we are and where we come from. For some communities, particularly those with long histories tied intimately to specific landscapes, the death of coastal forests represents losses that cannot be measured in dollars or quantified in scientific studies. Indigenous groups like the Lumbee see ghost forests as threats to cultural landscapes, places that hold meaning far beyond their ecological or economic value. The Lumbee people have lived in what is now North Carolina for countless generations, their history and identity woven inextricably into the land itself. The forests, rivers, and wetlands of the coastal plain are not just scenery or resources to the Lumbee. They are repositories of memory, sites of historical events, places where ancestors lived and are buried, landscapes that feature in stories passed down through families for hundreds of years. When these forests die and transform into ghost forests, it's not just trees that are lost. It's the integrity of cultural landscapes, the ability to walk where ancestors walked, to see what they saw, to maintain that tangible connection to the past that comes from sharing physical spaces with those who came before. Coastal tribes in North Carolina link ghost forests to the loss of sacred longleaf pine ecosystems, forests that once covered vast areas of the southeastern coastal plain and held particular spiritual and practical significance. Longleaf pine forests are among the most biodiverse ecosystems in North America, home to hundreds of species found nowhere else, but they're also tremendously diminished from their historical extent, reduced to a fraction of their former range by logging, development, and conversion to other land uses. The remaining longleaf pine forests are precious, both ecologically and culturally. For indigenous communities, these forests provided materials for basket making, traditional medicines, foods harvested seasonally according to practices refined over generations. They were places for ceremonies, for teaching young people traditional knowledge, for maintaining practices that define cultural identity. When longleaf pine forests in coastal areas succumb to saltwater intrusion and become ghost forests, these communities lose not just trees but irreplaceable cultural resources, places that connected them to their heritage in ways that cannot be recreated elsewhere. Ghost forests can disrupt oral histories tied to riverscapes and ancestral forests, breaking chains of memory and tradition that have persisted for centuries. Many indigenous cultures maintain oral traditions, stories and histories passed from generation to generation without being written down, kept alive through the practice of elders teaching younger community members, often in the very landscapes where the events described took place. A story about something that happened at a particular bend in a river, beneath a specific grove of trees, carries more power and meaning when you can actually stand in that location, when the landscape itself serves as a mnemonic device, a physical anchor for memory. But when ghost forests transform those landscapes beyond recognition, when the grove of trees becomes a stand of gray snags in a spreading marsh, when the riverscape changes so dramatically that it no longer resembles the place described in the stories, something essential is lost. The oral tradition can continue, the stories can still be told, but they lose some of their grounding in physical reality. The connection between past and present, between the events described and the landscape listeners inhabit, becomes attenuated, harder to feel and understand viscerally. This disruption affects not just indigenous communities but anyone with deep roots in coastal areas, anyone whose family history is bound up with specific forests and waterways. Think of the family that has owned the same property for 5 generations, where grandparents told stories about playing in certain groves of trees as children, where parents proposed to each other beneath particular oaks, where children learn to identify birds and plants from their elders. When those trees die and the landscape transforms, those specific sites of family memory disappear. The stories remain, but the places they refer to are gone. There's a particular poignancy to this kind of loss, different from the grief of losing a person but real nonetheless. It's the loss of continuity, the breaking of threads that connected present to past, the severing of relationships with place that help define who we are. Ghost forests remind us that coastlines are alive, not static boundaries drawn on maps but dynamic zones where land and sea interact in constantly shifting relationships. We tend to think of the coast as a fixed thing, a line where the ocean stops and the land begins. We draw that line on maps and treat it as permanent, building our homes and roads as if that boundary will never change. But ghost forests demonstrate viscerally that this is an illusion. The coast is always moving, always negotiating its position based on the balance between erosion and deposition, between sea level and land elevation, between freshwater flow and saltwater intrusion. In human terms, these movements might seem slow, changes that unfold over years or decades. But in geological terms, they're rapid, dynamic processes that never stop. The trees themselves, standing dead but still upright, serve as markers of this dynamism, evidence that the coast was once different and is actively becoming something else. And that change can be slow, sudden, and irreversible, a reminder that environmental transformations don't follow comfortable human timescales or preferences. Some ghost forests form gradually, trees declining over decades as salt levels slowly increase, giving communities time to observe and adapt, even if they can't ultimately prevent the transformation. Other ghost forests appear with shocking speed, entire landscapes altered in the span of a single hurricane, forests that looked healthy one month standing dead the next. And once formed, ghost forests rarely if ever reverse. The trees don't recover. The salt doesn't spontaneously leave the soil. Even if sea levels were to somehow stop rising tomorrow, the forests that have already died would remain dead. The changes are permanent on human timescales, written into the landscape for generations to come. This irreversibility is perhaps the most difficult aspect to accept. We're accustomed to thinking of environmental damage as something that can be repaired, cleaned up, restored. But you cannot bring a ghost forest back to life. You can only witness its transformation into whatever comes next. The cultural and community impacts of ghost forests challenge us to think about what we value and why, about what it means when landscapes that hold our histories and identities transform beyond recognition. They remind us that we are not separate from nature, not insulated from environmental change. The forests that die are forests we knew, forests our families knew, forests that were part of our sense of home and belonging. Their death diminishes us in ways that are hard to articulate but impossible to deny. It forces us to grieve not just for trees but for connections severed, for continuity broken, for places lost that can never be recovered. Yet even in this grief, there is something to be learned. Ghost forests teach us about impermanence, about the inevitability of change, about the importance of cherishing what we have while we have it. They remind us to pay attention to the places we love, to notice them, to remember them, to pass those memories and the importance of those places on to those who come after us. They challenge us to think not just about preserving what exists, but about how we relate to landscapes that are changing, how we maintain cultural connections and historical memory even as the physical settings of our stories transform. As you rest now, in the quiet darkness of approaching sleep, think about the places that matter to you, the landscapes that hold your memories and shape your sense of who you are. Think about the trees you've known, the rivers you've walked beside, the forests you've explored. Hold them in your mind with gratitude and awareness, recognizing that all things change, that no landscape lasts forever, but that the connections we form with places, the memories we carry, the stories we tell, these have value beyond the physical persistence of the places themselves. Let these thoughts carry you gently into sleep, into dreams where forests stand green and vital, where change is held at bay, where the coast remains for a time exactly where we remember it being, safe and familiar and home. If these sounds helped you find a moment of peace today, please consider subscribing to join our quiet community. A like or a comment helps these stories reach others who might need a rest. And if you know someone seeking a hushed horizon, feel free to share this journey with them. Until next time, sleep well.